Hello, everybody, and welcome to the week 8 video for Math 4400. So just some quick reminders. Your homework 7 will be due on March 13th. That's the Monday after a break at the usual time of 11:59 p.m. Then the quiz on this video will be due on March 14th. That's the Tuesday after break. And again, at the normal time of 8:30 a.m. Your second exam is also that week. So it's on Thursday of that week, which is March 16th. And the info about that exam is on Canvas, like sort of like the template, so you can see what kind of problems will be on it. I encourage you to go over that before the review session on March, so that's supposed to say 3/14, so on March 14th, which is Tuesday after break. So in that class, we're going to have a review session, just like we did for exam 1. So again, it will be on Zoom. The link is available on Canvas, and I will record that session and post it. I'll start by just going over the exam, going over some examples of similar problems to the types of problems that will be on the exam. And then at the end, there will be time for questions if you have any. Okay, good. And so that's all the logistical announcements. So mathematically, we had some key takeaways from this week. So on Tuesday, we talked about primitive roots. And the big things were like, how do you find them? Like if I give you sort of, especially like if I give you like a prime number p, like how do you find a primitive root mod p? And so we sort of saw there was sort of a nice criteria where you only had to check that certain powers weren't 1, and you'll do that on your homework to find some primitive roots. And then we also wanted to know, well, why were we finding primitive roots? We were finding them because they were useful for solving equations. So we wanted to we learned how to use them to solve sort of congruences, and particular congruences involving powers. So you'll have some exercises. You have some exercises in your homework this week where you first you find a primitive root and make a table of its powers, and then you use that to solve a bunch of different congruences modulo that prime. And so that's what primitive roots are good for. And then on Thursday, we talked about cryptography. In particular, we talked about the Diffie-Hellman key exchange and like how you could use that to like set up as shared secret to do a shift cipher. And we talked about RSA. And so that was the one that sort of let all of you send me secret messages after I sort of just posted one piece of information that I could only decrypt. Okay, so those are the main things we talked about this week. I mean, there's a connection. I mean, so primitive roots somehow play a role in understanding how these cryptography schemes work, because I mean, so both these cryptography schemes involve raising some element to a large power. So I'm going to say a little bit more about that right now. In particular, I want to talk about the following theorem, which we stated in class on Tuesday, but didn't justify. So this says there's a primitive root modulo n exactly when n is either 2, 4, or a power of an odd prime, so p to the k for p an odd prime, or 2 times the power of an odd prime. So like 2 times p to the k for p an odd prime. And those are the only times you're going to have a primitive root modulo n. So for every other n, there won't be a primitive root. And we saw some examples like illustrating this on Tuesday. So for example, we saw there's no primitive root mod 8. We saw there's no primitive root mod 12. Then we saw lots of examples where there was a primitive root modulo a prime number. Of course, that's always going to be true. The case of p prime is the most important case. And what's really important in this theorem is sort of not to understand why this is exactly when it's true, but more to understand why it is true when p is an odd prime, or sort of it's not too much more difficult to see why it's true when p is a power of an odd prime. So we'll talk about that too. So that's what I'm going to explain in this video. It's a fun exercise, especially if you do happen to know a little bit more group theory than we've talked about in class, to see why it doesn't hold for like a product of like 2 odd primes. So like, why doesn't it hold for like 3 times 5? Why is there no primitive root modulo 15? But we're not going to talk about that today. Okay, so let me sort of break that apart. So we're going to show why primitive roots exist modulo prime powers. And well, step 1 is to show that a primitive root exists when p is prime. And in fact, we can be a little bit more precise, and it's useful to be more precise because it helps explain some important things related to cryptography. So we can say that if I take any divisor of p minus 1, so remember, sort of a primitive root is sort of an element of UP, so the units mod P, such that it's P minus first power is 1, but sort of no lower power is 1. So in other words, an element of UP of order P minus 1. But I'm just going to say more. I can say if I take any divisor P minus 1, then there are exactly phi of D elements of UP minus 1 that have order, so that's supposed to say order D. So if I want to know how many elements of order D there are, where D is divisor P minus 1, well, then there are phi of D elements of that order in UP minus 1. And so, well, every element has, so this is something we talked about on Tuesday, but because by Fermat's little theorem, sort of every element to the P minus first power is 1 mod P, we know that the order of any element does have to divide P minus 1. So we know these are the only possible orders, and then the question was, how many elements are there of each order? So this is the fact I'll actually explain to you. I'll explain why this holds. But let me tell you why this is a useful sort of refinement to know. I mean, basically, this tells you that, for example, like when you're doing Diffie-Hellman, we sort of have this two pieces of information we have to pick. We have to pick P, a prime number, and G. And so G is sort of our base of exponentiation when we sort of try to establish a shared secret. Well, this is good, and sort of Diffie-Hellman works well, as long as the order of G is pretty big. We don't actually need, we don't need G to be a primitive root, although that's sort of like the best case scenario is if G is a primitive root. But all we need to know is like the order of G is pretty large. That will sort of make it sort of hard to compute, like hard to sort of do this reverse step where you see a power of G and you sort of ask what power is it? That's sort of what someone would have to do to crack the code. And so you want to avoid sort of making a choice where G has small order mod P. But and this statement sort of tells you like there aren't very many elements that have small order. Like, I mean, if I sort of have order 5, like there are at most 4 elements of order 5, because 4 is phi of 5. So somehow this statement, like this more precise version, tells you like you don't have to worry too much about this, because they're just like, if you pick G at random, like there aren't that many choices of G that would end up giving you an element of small order. Okay, so that's sort of helpful to know theoretically when you're implementing cryptography algorithms. Okay, so we want to prove this statement. We want to prove that there are phi of D elements of order D in UP minus 1. To do that, we're going to need a lemma, and this is just a lemma about the phi function. So Euler's phi function. So remember, phi of m is just the number of elements between 1 and m that are coprime to m. And so the lemma says that if I look at all the divisors of n, and I add up the values phi of D over all those divisors, then what I get is n. Okay, so this is sort of a nice, pretty statement. Let's sort of check just like what this is saying in one case, like, e.g., if n is equal to 6, then we're getting the sum. We're getting, what are the divisors? Well, we're getting phi of 1 plus phi of 2 plus phi of 3. So 1, 2, and 3, those are the divisors of 6. That's supposed to be equal to 6. Oh, sorry. 6 is also a divisor of 6, plus phi of 6. So that's supposed to be equal to 6. And so phi of 1 is 1. Phi of 2 is also 1. Phi of 3 is 2. And then phi of 6, well, the only elements coprime to 6, less than 6 are 5 and 1. So phi of 6 is also 2. And so we're getting 1 plus 1 plus 2 plus 2 is equal to 6. So that's what this formula says in the case when n is equal to 6. We're not actually going to use the formula in this form. The way we're going to use this formula is in the form that says phi of n is equal to the difference between n and then the sum of phi of D over all the proper divisors of n. But this is just, I moved part of this. I just sort of rearranged part of this equation to the other side to write that. Okay, but so why is this sum equal to n? Well, I mean, basically, this is just a counting argument. You can sort of see that phi of D is counting a certain thing, and then so when you sort of put all those things together, you get just n things. And so how do you do that? Well, if you think about it, and this is sort of, I'll leave as an exercise for you. I mean, phi of d, normally I think of it as counting the number of elements between 1 and d that are co-prime to d. But I also could think of this as being counting the number of elements in the interval from 1 to n, whose GCD with n is equal to d. So I get that sort of just by sort of, I take sort of some element between, sorry, I should have said, this is supposed to be n over d. So to do that, I sort of just take n over d and I multiply it, like to sort of see why that's the same. If I have like some element between 1 and d that's co-prime to d, well, I just take this n over d and I multiply it by that element, and that will give me a number now between 1 and n, whose GCD with n is n over d. So that's the idea. Okay, but I mean, since as d goes through all of the divisors, like n over d goes through all the possible GCDs. So n over d also goes through all the possible divisors. So it's sort of going through all the possible GCDs a number can have with n. And so sort of as I go through all of these d's that divide n, I'm really sort of counting exactly once every number between 1 and n. So I'm getting n things. So that's sort of the idea of why this equality holds. Good, so I'll move on accepting that. And so then how do I use this lemma? Well, it's going to be sort of a fun way. So what I want to do is I want to actually define some polynomials. So these are called cyclotomic polynomials. And the key property of these polynomials is going to be, like I'm just going to define a polynomial sort of capital phi sub n of x. And the roots of that polynomial are going to be exactly the elements of order n. So if I sort of capital phi n, like its roots will be the elements of order n in sort of UP or in FP cross. So I'm gonna, when I define these polynomials, I'm going to think of them as having coefficients in the field with p elements, so in FP. Good, so how do I define these? Well, phi1 of x is just x minus 1. So the only root of that is 1, and well, 1 is the only element whose first power is 1. So that's good, sort of, that's what this should be. And then, well, if I want to sort of more generally, like if I want to sort of have an element of order n, well, saying an element has order n is saying x to the n is equal to 1. That's part of it. So x to the n will have to be equal to 1. So it's in other words, an element would have to be a root of x to the n minus 1 if it has order n. But to have order n, like n has to be the first power that gives you 1. So that means sort of you can't be a root of like any smaller sort of like x to the d minus 1 for any smaller d, so for divisor of n. Well, so we can sort of capture that by saying we should like look at x to the n minus 1, but then we should divide it by all of these smaller, like these cyclotomic polynomials, capital phi of d, where sort of d divides n, but is not equal to n. So sort of where d is a proper divisor of n. So this is like an inductive description of these polynomials. So I sort of start by saying what phi1 is, and then sort of the formula for like phi of a, say q is a prime number, sort of depends on what phi of 1 is. So this formula sort of tells you that sort of now, if I know what phi of 1 is, then sort of phi of a prime number q, well, I take x to the q minus 1 and I divide it by x minus 1, because 1 will be the only proper divisor of that prime number. And I'll get this polynomial x to the q minus 1 plus x to the q minus 2, and so on, all the way down to 1. This is sort of a formula that should be familiar from like looking at geometric series. So this is what you get sort of for q prime. So if this number down here is prime. And then once you know what this is for prime numbers, like then you can sort of define it for like the product of two prime numbers, because you'd sort of take x to like the pq minus 1, and then you divide by sort of phi of d for all proper divisors. So like the proper divisors would be 1, p, and q, if n was p times q. Okay, so that's the idea. This is sort of an inductive description. And sort of from this inductive description, you can see that the degree of phi n of x, this capital phi n of x, is actually just little phi n of x. So now the degree of these polynomials is this Euler function phi. I mean, so like phi of 1 is 1, this has degree 1, that's good. Like when q is a prime number, the phi of q is q minus 1, and that's good. This is a polynomial of degree q minus 1. And then sort of more generally, you can sort of see this degree formula you can sort of prove it by induction using this lemma right here. So in particular, this formula for phi of n. So like this is saying phi of n is sort of n minus the sum of over all the divisors of n of little phi of d. And so somehow you're taking the n up here and you're subtracting sort of all the things in the denominator, which you already know their degrees agree with phi of little d by sort of the induction. So that's sort of how it's working, how this induction works. And sort of while you're doing that induction, actually, you can sort of do a little bit more. Sort of at the same time, like you can sort of prove this key property of these polynomials that I said, which is that the roots of phi of dx in FP, these are going to be exactly the elements of order D in UP or FP cross. So the units mod P. So somehow we get sort of the degree of this thing, and we get that its roots are exactly sort of the things we're looking for, the elements of order D. But that sort of proves the statement. I mean, that says that, well, the elements of order D are roots of this polynomial, which has degree D. And so that thing has D roots. Well, there's sort of one thing I have to check. I have to check that sort of it actually has D roots. So I need to know that this polynomial sort of splits completely into linear factors that has D roots. But that's not so hard because I know that x to the p minus 1, so this polynomial, well, this is actually just the product over all a and FP cross or an UP of x minus a. And this is because, well, this is a degree p minus 1 polynomial. There's sort of p minus 1 things. And by Fermat's little theorem, each of these is a root. So I know sort of if I have, I can have, by Lagrange's theorem for polynomials, I know I can have at most sort of p minus 1 roots of this degree p polynomial. So this is sort of really the complete factorization. Good, so now, and so this polynomial splits completely into linear factors. But the polynomial phi, so if d is divisor of p minus 1, well, the polynomial phi d of x divides the polynomial x to the d minus 1. I mean, this is basically by definition, I got this polynomial, like I get phi n by taking x to the n minus 1 and dividing by some things. So this polynomial divides x to d minus 1, but then it's not hard to check that sort of because d is divisor of p minus 1, x to the d minus 1 divides x to the p minus 1 as polynomials. Like this looks a lot like sort of this kind of computation. Okay, but now sort of if you have a polynomial which divides some other polynomial that splits completely into linear factors, well, this just has to be sort of some product of like some subset of those roots. So this thing also splits completely into linear factors, and so it has phi of d roots in FP, which is exactly why we want to say, because the roots of this are exactly the elements of order P of order D in sort of this group UP of units in FP cross. Okay, so that was a lot to go through at once, so you might not have followed it completely, but somehow this is a fun idea. So you're playing off sort of the structure of polynomials versus like this multiplicative structure to see what's going on here. So it's sort of a fun proof. I mean, these cyclotomic polynomials are sort of very interesting. I mean, we don't have to work like with coefficients in a finite field actually to define these. So somehow this also makes sense like with integer coefficients and well, actually, yeah, maybe if you're interested, you should go look up the Wikipedia page on cyclotomic polynomials. There are sort of some fun questions you can ask about these, and sort of fun to compute some of them. Okay, but sort of moving on, so we've established this result that there are sort of phi of d elements of order D in UP, where D is any divisor of P minus 1. And so this, in particular, this tells us there is a primitive root. So when we just take D to be P minus 1, there are phi of P minus 1 elements of order P minus 1. And so those are the primitive roots. Great. So now the last thing I wanted to talk about is sort of how you sort of then go up to see that there are also primitive roots modulo any prime power. So I want to go from P to P to the K when P is an odd prime. So what does that mean? Well, what am I trying to do? So phi of P to the K, that's P to the K minus 1 times P minus 1. This is the formula we've seen. And so I'm looking for an element of order, sort of P to the K minus 1 times P minus 1 in sort of U P to the K. So in the group of units, mod P to the K. If I'm trying to produce such a thing, well, I could use a trick. And actually, sort of if I want to get such a thing, what I really need to do is I want to make an element of order P minus 1 and a different element of order P to the K minus 1. And then when I multiply them together, actually their product is going to have order P minus 1 times P to the K minus 1. And so the reason that's true is somehow because the GCD of P minus 1 and P to the K minus 1 is 1. So somehow, and this is sort of a general fact about orders of elements that you can check. I mean, somehow it's an exercise to check this, but it's not a very difficult exercise. So when we have sort of two elements of sort of whose orders are co-prime, then their product has order, so just the product of those two orders. Okay, so this sort of breaks down the problem to sort of two different parts. We need to find an element of order P minus 1 and an element of order P to the K minus 1. But now we can solve those pretty easily. So we know that we have, so for the element of order P minus 1, I mean, we know already that if we look mod P, we have a primitive root. Well, whatever, and so that's an element of order P minus 1. So let's call it zeta P minus 1. Wait, sorry. So we have a primitive root. Let's not call it zeta P minus 1. That'll be the lift. So we have a primitive root mod P. But sort of that primitive root, like it is a root of the polynomial x to the P minus 1 minus 1. Just by definition, I mean, sort of it's a root of that polynomial. It's P minus first power is 1. And sort of it's a simple root of this polynomial mod P. So Hensel's lemma tells us that we can lift it to a root mod P to the K. So we lift this root of x to the P minus 1 minus 1 mod P to a root mod P to the K, and we're going to call that lift sort of zeta P minus 1. So zeta is sort of what you use for like roots of unity. It's a lot of use for roots of unity. So elements whose power is 1. Good. So we get this element zeta P minus 1, and sort of its P minus first power is 1. But on the other hand, like mod P, it has order P minus 1. So you really see that actually like mod P, like in P to U P to the K, it also has order P minus 1. Because somehow like it couldn't have a smaller order because then mod P would also have a smaller order. Good. So this gives you your element. So Hensel's lemma is what gives you your element of order P minus 1. And then the last thing we need to do is find an element of order P to the K minus 1. And I claim that actually 1 plus P has order P to the K minus 1 in sort of this unit group U P to the K. And so basically the idea is if you like look at 1 plus P and you raise that to some power A, well, if you sort of expand that out, that's going to look like 1 plus A times P plus some other stuff that sort of involves powers of P and then sort of binomial coefficients with A. Like sort of like the next term would be like A choose 2 times P squared and so on. And sort of the key sort of thing that happens here is if you look at like the stuff you get out here, sort of it's always going to be divisible by a higher power of P than sort of the power of P that's dividing A times P. So for example, if A is co-prime to P, then sort of so everything here sort of has like a P squared, like at least a P squared. So good. Like if A is sort of like say A is equal to P, well now we get sort of a P squared here. But then if you sort of compute out like P choose 2 and P choose 3 and so on, like those are like now these binomial coefficients sort of become divisible by P too. So that's sort of the idea of the kind of thing you have to check to sort of see the statement is true. But I sort of really, I'm telling you it is. So 1 plus p to the a is, if you work it out, sort of just 1 plus a times p times something divisible by plus something divisible by a higher power of p. And then it's sort of like, then you're just asking sort of what's the smallest power a such that this is 0 mod p to the k. Well, since this is sort of always divisible by a higher power, like the smallest a is going to be just when a is p to the k minus 1. So the smallest power divisible is sort of congruent to 1 mod p to the k is a equals p to the k minus 1. So that will give you 1 plus p to the k minus 1 plus sort of something that's divisible by p to the k. Okay. So this part actually is the step that breaks when you do p equals 2, when you say p is an odd prime. I mean, this claim I made that this part is always divisible by a higher power of p isn't actually true in that case. Good. So that's sort of finishes. We have our element of order p. We have order p minus 1, and we have our element of order p to the k minus 1. And so then sort of our element of order, our primitive root is just sort of zeta p minus 1 times 1 plus p. So for example, like if you take, yes, let's do an example. So find a primitive root mod 9. Well, we'd start by sort of taking 2 as a primitive root mod 3. And then we sort of lift it to a root of x squared minus 1 mod 9. And so to do that, well, we're looking at sort of which number, sort of which shift of 2 by 3 sort of satisfies that. And it's going to be 8. So we get sort of x equals 8. So 8 squared minus 1 is 0 mod 9. So let me say we get sort of zeta 2 is 8. I mean, sort of, it's not surprising. Sort of here, like just minus 1 squared is always 1. So that's sort of what we're getting here. And then we're looking at 8 times 1 plus 3. So p is 3. So this is 8 times 4. So this is 32, which is 5 mod 9. So this is supposed to be our primitive root. And well, 5 squared, this is 25. So that's 7 mod 9. So 5 cubed is equal to 35 then, which is 8 mod 9, and when we're done. So 5 is a primitive root mod 9. So here we were checking. I mean, sort of this proof we went through told us that sort of 5 was going to be a primitive root mod 9. So if you believe the proof, then you believe this case. But here I'm just checking that 5 really is a primitive root mod 9. To check that, we just have to check that sort of so phi of 9 is 6. So we had to check that 5 squared and 5 cubed was not 1. And sort of in both cases, it wasn't. So we're good. Okay, so 5 is a primitive root mod 9. And this method works out. All right, I'll stop there. I hope you enjoy your break, and I will see you the week after spring break for the review session on Tuesday.